We're into the afternoon session now, and the first talk this afternoon is from our other platinum sponsor. Again, we do thank our sponsors. We couldn't put it on without our sponsors. And the second platinum sponsor is Cadence Design Systems, and our speaker from Cadence is Nick Heaton, who is a distinguished R&D engineer. Nick works in the Cadence Systems and Verification Group as a distinguished engineer responsible for SoC verification, especially around ARM-based designs. And the title of his presentation is Exploring How the Internet of Things is Changing the Verification Challenge.
Thanks, Mike. So my challenge this afternoon is to keep you all awake for 30 minutes. Seem to have got the graveyard slot again. I've been at quite a few of these and presented at quite a few, and historically we've tried to give, as the title of the conference states, what we think is, you know, the future, where we're going as a company, where we see the challenges. So this year I wanted to do something similar, but really give a little bit of background on why we think the Internet of Things is actually changing the job of the verification engineer. I think the dominance of the mobile phone industry in terms of the way EDA builds tools is still the case. We still focus on mobile hugely, but IoT is actually changing things. So what I want to go through, why is this not in presentation mode? So I'm going to quickly go through what I mean by IoT, because I think there's maybe some confusion. I won't take very long, and look at some historical trends. One of the few good things about us being as old as I am is that I've actually seen the evolution of the industry from the first design I did, which was gate level schematics. Okay, so things have changed quite a lot since then, thank God. And then really look at where we see these new challenges being, and talk about a few of the things we're doing. I've got 30 minutes. Cadence is doing a huge amount of new development on all kinds of things, some of which I'll put up here, but I can only give you a certain taster of a few of the things we're doing. Okay, so what do we mean by IoT? I've been very lazy here and stolen someone else's slides, because there's hundreds of IoT slides out there. Thank you, ARM, for the promotion. There's a lot of people talking about it, but I quite like this one, which really describes IoT as the three things: as sensors, connectivity, people, and processes. And obviously, the bit in the middle is kind of where we've had a lot of focus in the last 15, 20 years, is the connectivity, mobile phone, wireless communications, wired communications. That part of it has really been a huge focus. But it's at the two other ends, I think, really, that IoT starts to change some of the challenges. Sensors, obviously, we have a lot of mixed signal challenges, and that's obviously a strength of Cadence. We've got a lot of mixed signal technology, but there are other challenges I'm going to talk about in a minute. When we start putting devices into cars and medical equipment and this kind of thing, it kind of changes from being maybe what was a PPA focus for a large number of years, power performance area. We suddenly have other things. Somebody, I think it was Mike Bennett, said, you know, quality is not optional for aeronautical. You know, and there are things that suddenly change as a verification guy. What do I spend my time doing? What do I care about? Is it just functionality, getting out the door? No, it's not that anymore. Okay. Connectivity, well, that doesn't stop evolving. So we may have done a lot of work on mobile, but there's more and more wireless standards, short-range standards, high-speed standards coming along, and again, managing that complexity, very difficult. And then at the back end, really, what makes IoT attractive is what happens kind of in the back office. We may have, you know, Fitbits and whatever other sensors and in our lives, but ultimately what makes them useful is the bit that sits out of sight. And for us, Cadence, that's also one of the big areas. You know, you need the cloud infrastructure, you need high-performance servers, you need high-performance networking, all of the things that are going to make this actually functional. Okay, so they're the kind of areas that we see are affecting verification challenge. I want to talk, and I'm going to spend very little time on this because you're all probably familiar with this, but I want to try and draw out some 3 things that I think are also ongoing that we've been experiencing for some time. And this is just a very simplified view of the world, but if you look at the gate count, logarithmic growth over 20, 30 years, the amount of custom IP we do is really sort of stayed the same, but as a proportion of the design. There's an awful lot of IP reuse, and so this has really driven SoC integration and the challenges of integration. It's not just plugging the IP together anymore that's the challenge. It's a lot of the IP interacts with each other. So the system level challenges in verification are getting bigger and bigger, and that creates scalability. So if I need to do more verification of the full system, what do I need to do that? I can't just use a couple of simulator licenses and do all of this. It's beyond the scope of that. And this is an area I'm certainly focused a lot on is SoC verification. I'll give you an example. So for example, PCIe. Has anyone actually had any experience of PCIe verification? Because they've probably got grey hair or no hair, right? Right. We have. Right, it's a nightmare. PCIe Gen 4 now gives us capabilities that connect the MMU, the SMMU in your design with devices outside. So how do you verify? You can't just verify each of those pieces of IP completely in isolation anymore. You have to start saying, well, I need some software to configure these complex IP, and I need to plug them together, and I need something that mimics the outside world to even start to just exercise those capabilities. So those kind of things are really tough. Okay. Again, completely off the top of my head, and I'm talking here, I guess, about the leading edge designs, but the number of cores, processor cores in design has just kept going up. And, I've been through this, as I said, I'm old, so I've got experience all the way back here where there were no cores. In the early days, great, no processors in there, it makes it easier, right? But this creates a big software aspect to verifying the SoCs, right? And it's not simply a matter of, as I said earlier, PPA, this is the way ARM would define a processor. We've optimized this processor to run at this speed in this technology, and it takes this many square millimeters. And you could kind of say, okay, so long as I get that right, my system will perform. Well, now when you've got 8 plus 16 plus processors plus highly intelligent peripherals that require their own significant bandwidth, how do I know that that's going to perform? So system PPA is a hard problem, and making sure system performance is achieved is one of the challenges that we see. And there's a huge, as I said, there are some things like coherency has become ubiquitous. It's being pushed onto the whole of the SoC market that you will expect to have to do some I/O coherency maybe. Virtualization is now becoming common. These are tough things to verify. Now you don't necessarily want to completely verify the MMU IP itself, but it's the integration with your interrupt controller and other things. And methodology trends. The first chip I designed, I wrote all of the tests myself. I designed the chip, wrote all the tests, all directed tests, and did everything, basically, the floor plan, the whole lot. Now it's just beyond the scope of people to do all of that. But we've evolved from a directed testing approach. ERM and UVM and OVM evolved from the 2000s up to the present day, and it's still going on. We're not finished with it. IP is still being developed, new IP is still being developed, still being used. But what we're seeing in the last few years, and we talked about this probably 2 or 3 conferences ago, about the need for more use case testing. So you can't verify an SoC exhaustively. It's way beyond the scope of all the simulators on the planet. What you have to do is focus in on key use cases and give the, ideally give the knowledge to help you create those use cases. Creating them manually is very hard. Okay? So these are the kind of trends that we see, and obviously it was mentioned earlier in the mentor presentation, portable stimulus is one of the things that's coming. This is, Xcelera accept that this is a coming need, and there's a standardization going on. Cadence has been heavily involved in that. I'm going to talk a little bit more about that in a minute. Okay, so what are the challenges? Well, you see here security, security, security. This is something that's really, at the last ARM TechCon was like almost every presentation was about security. There was a great presentation at DAC last year from Infineon about the fact that cars currently have hundreds of processing elements in them and they're completely non-secure. Car hacking is a real thing, and how do we move forward to stop that? And this is true of all of the IoT kind of aspects at all the places, in the sensors, in the connectivity, in the back office. Okay. Mixed signal, and obviously scalability of mixed signal. So this is something we are working on. I'm not going to be able to talk about it today, but it's something that's coming. That's very interesting. As I said before, there's still plenty of new protocols evolving, and building complex VIP, as somebody said earlier, is a tough thing, but that's going to continue. We don't see a let-up in that. If we extract what really the big challenges we're identifying and working on, we're looking at certainly security, because it affects IP. There's a hardware aspect to it, there's an integration aspect to it, there's a software aspect to it. Functional safety, we have a whole program going on. Somebody already from Synopsys talked a lot about functional safety. I'm not going to touch on that today, but it's definitely something that's changing. Verification challenge, if you haven't done functional safety, there's a whole new paradigm you have to learn. Simulation scalability, this has been something that there's insatiable demand for simulation capacity in the world. The number of simulators is just continually growing, and there's no sign of that letting up. Performance analysis, as I said earlier, things like PCIe, being able to do system-level performance analysis is a tough thing. And you might assume the architects do that, but they might do it on models. You need to concern yourself, if that was what the architects expected, did all the IP we bought in deliver what the architect expected? Because it's unlikely you've developed all the IP yourself, right? That's quite a tough problem, and generally gets pushed onto the verification people because it's RTL, it needs to be cycle accurate. So I'm going to talk about three key things. We made a couple of announcements very recently, so it's pertinent to this presentation. One of them was a new simulator. So if you look at the history of simulation, and as I said, I go back to the days of even pre-Verilog XL, you had interpreted simulators. In about the mid-90s, we went to compiled simulators. And that was a big leap, and we've managed to live with that for a huge amount of time, 20 years. And in part, I guess, constrained random verification helped us manage living with the limitations of simulation. Because instead of running one long simulation, somebody earlier said, constrained random's dumb. Well, it's not that dumb, because we can take a test and run it 100 times with different random seeds is the equivalent to running it 100 sequential times, right? But we can run that in 100th the time. So we've kind of managed parallelism through UVM and constrained random in a way, but some of the simulations you can't get away with running them like that. Video or things that need long sequences, iOS boot sequences, these are simulations you always have to run. Gate level, very slow. DFT, very slow. Okay, so we introduced a parallel simulator just a couple of months ago, which was part of an evolution from an acquisition we made last year. Rocket-Tick was an Israeli startup that had been around for quite a few years, had an established parallel simulator that was being used at a number of big customers. We acquired it and we've integrated it, refactored the whole architecture of the simulator. So now that you get the best of both worlds, and you get speed up depending, there's some variation in these numbers because I'll explain in a minute why. There's not a linear speed up, okay? So it's all to do with the activity in the design. So if we take a look at how this works, the new simulator effectively has a multi-core engine and a single-core engine. And depending on how your test bench and design is constructed, it partitions pieces of it to run either single-core or multi-core. Okay? So you get all the best bits of Incisive, so it runs all of the Incisive previous use models, everything that you could do with Incisive, whether it's System C or VHDL, Verilog, System Verilog, E, all of those are supported still just as they were previously, but you can actually run pieces of your design, mostly RTL, okay, so that's the bit we can speed up, okay, because it's RTL or gate level. You can parallelize the event queues for that kind of architecture. So what this gives you is you know, a set of use models where you're still going to run single core. There's no question you're going to run single core simulation for UVM test benches. That'll probably be the case. But for the key simulations where you need to run for longer, where you need to run gate level, where you need to run DFT, you've got an option of then running it considerably faster. Okay, and here are some of the examples. So my team did a lot of test cases of this simulator prior to the acquisition, but also post-acquisition, looking at what kind of simulations this is good for. My team builds ARM subsystems in-house to actually test a lot of things we do, because a lot of our customers also build ARM systems. And so running boot, for example, on an ARM system, you don't have such a high event density and you don't get such a massive speed up. But when you start to run multiple cores and run multiple activities concurrently, which is what the SoC is designed to do, you get a bigger speed up. So the nice thing is you can combine this with a piece of technology I'm going to talk about later, which allows you to generate tests for multiple cores, okay, software-driven testing. Okay, so that's one piece of technology. We announced also recently a new FPGA prototyping. So remember we talked about scalability, and there's an awful lot more software being run on SoCs. FPGA prototyping, as somebody said, I think from Sequent said earlier, it's an essential part of the process of development and validation. And you know, this is really where a lot of the software bring up and a lot of software aspects are validated. Now, FPGA prototyping historically is very hard to do because you've actually got to generally modify your design to map it onto an FPGA. The memories are not the same. There's not the same gate count opportunities. The clocking may be different. Okay, so one of the things we wanted to do was try and minimize that cost, and we already have a Palladium front-end compiler, so we've done a lot of work to provide exactly the same front-end for our FPGA prototyping as we do for our Palladium. What does this mean? Well, you know, as I said, it's hard to do. You can spend months bringing up an optimized design for an FPGA. The challenge then is also, if you find a bug in the FPGA when you've done all of this modification of the RTL, how do you correlate it back to a simulation to try and debug it if the debug in the FPGA is not up to what you really need? So with a common front end, we're able to provide a much more rapid path to FPGA prototyping. Now, you might ask how we do this. I'll talk about that in a minute. But ultimately, the key thing here is no RTL modifications needed. So that's why it allows us, once you've got a design running in Palladium, you can very quickly get to FPGA execution. So how do we do that? Well, we automatically convert latches, tri-states, and clock trees for you. So there's an automatic step. And the key thing is a modeling mechanism to allow you to model memories. Memories are prevalent everywhere in your designs, right? And how do you map those to an FPGA memory? Well, we have a flexible memory board that allows you to automatically convert and support LPDDR 2, 3, 4, whatever, NAND flash. So this is how we get around that problem. And it means you can also partition automatically as well. So this is not a single FPGA solution, it's a multiple FPGA solution. Okay. So we've talked about two engines that are really designed for SoC verification. As I said earlier, a key component of both, whether you're running on Xcelium or you're running on FPGA, there's going to be some software. And the third thing I want to talk about is portable stimulus and how we're addressing that. So there's a need for reuse in an SoC development across both platforms, so from early virtual platform, simulation, emulation, FPGA. You want to reuse tests across these. You don't want to have to rewrite software or rewrite UVM tests if you possibly can avoid it. You also have different goals of the different team members. There is also different scopes. So are you testing IP? So are you testing one of the blocks here or a subsystem? Are you doing it with the OS or without the OS? Okay, so there's a lot of reuse you would like to have, and it's quite a complex problem. So how do we solve this? Well, we launched a tool called Perspec a couple of years ago, and we've been evolving it ever since. And what it does is it allows you to build an abstract model of your system, whatever it is. It's a very simple, lightweight, abstract model, but it then allows you to define use cases and target them. And the targeting can be either C tests, SV tests, whatever you want to generate. So we can create a model, create a use case, and then target it either for UVM or for software or for a mix of both. Okay. Now this is very powerful because it allows you to build, for an IP, you can build a test that has a software perspective for the processor interface and a UVM perspective for the VIP, and then migrate it to the SoC level. Okay. Now, this is something we're seeing a lot of take-up with. It's becoming hugely popular, and we're seeing customers getting massive productivity gains, and I'll give you a brief explanation as to how they get those gains. The key thing is a lot of these SoCs need tons of bare metal software just to validate that they're going to be good before you tape out. That's a huge effort. How do we do this? How do we make this valuable? Well, we capture goals of a use case. Now, one thing I want to stress here, this is not a graph-based tool. You see graphs here, people think it's a graph-based tool. This is not. This is a visual way of describing the goals of my test. It says I want to get something on my video, and it's got to come from memory, and I also want to transmit it on the modem. I've not said how it's actually going to do that. Okay, that's my goal. What the tool does using the abstract model is it generates a use case. And effectively, it generates a graph that is one solution to this. And it can generate multiple solutions if there are degrees of freedom that it can use. What that means is, and if you look at this graph on the right, these 4 things I've specified appear in the solution, but the tool has filled in all of the control and data paths into that to give you a valid solution. In other words, it'll say, I need to get data from somewhere. So it said randomly, I'll pick a camera capture. I'll capture the data on a camera, put it in memory, convert it to the right format, and then send it to the display in the modem. Okay? Now those degrees of freedom mean that if I regenerate this again, I may get a completely different graph, and I can run some of these things on different cores or a single core, and the tool allows me to do that. So you can very quickly generate very complex tests that would be very hard to do in a manual way. The other thing is we're building reusable content, so kind of the proof of the pudding of this portable stimulus is if we can build portable content, then it by definition is working. So we have an ARM library that's available today that allows you with a spreadsheet say I've got this ARM system, and it will then give you software tests out of the box. You don't have to write any code, you can start running tests without writing code. Now you can add to that and mix and match your own tests with the pre-packaged ones. Okay. So what does Perspec give me? It gives me productivity with a UML type use case diagram, out of the box content, and it'll run across simulation, emulation, FPGA, post-silicon. Okay. So that's kind of my brief insight into things we're doing. Thank you for listening.
Thank you, Nick. Thank you very much.